Exercise 1.1, question number 32. So number 1, R equals, so we're given the set A. So it contains of the set of all whole numbers from 0 to 17, and R is this relation here. This question, it can be proved in two ways. Because the set A is finite, we can just list all the elements of A, and then also we can list all the elements of R, and then we check for all the elements. So let's try to prove using the first method by listing all the elements of A and R. So A equals to X belongs to W, so the set of whole numbers, such that this X is greater than or equal to 0 and less than or equal to 17. So this means this is equal to 0, 1, 2, 3 and up to 17. So that's A. Then we write the value of R. So R is equal to AB, such that so modulus of A minus B is a multiple of 5. Okay, so in this set R, so what kind of elements would be there? Suppose I take the first be 0. Okay, so the A I take to be 0. Then what can be the value of B? So can B be 2? No, because if you take 0 minus 2 modulus, this is 2, which is not a multiple of 5. So the numbers that you can put for the value of y here are only those which, if you subtract with 0, you get a multiple of 5, like 0, 5. Then comes 0, 10. Then comes 0, so 15. Okay, so those are the first 3 elements. So there are no more elements starting with 0. Then let's try, what if we start with 1? So this continues here. So but I'll write it down here. So 1. So what is that number which when subtracted with 5 gives a multiple of 5? Okay, first of all here we're missing some number here. That element is 0, 0. Okay, so here we must have the element 0, 0 before, as well here, because 0, 0, even 0, 0, if you subtract 0 and 0, you do get 0, which is a multiple of 5. So let's just write down first 0, 0. So I have here 0, 0, which works, then also 0, 5, then 0, 10, and then 0, 15. So that's all. Then we come to 1. So 1 will be a multiple of 5, because 1 minus 1 is 0, again a multiple of 5. Then 1, 6 will belong to R, because 1 minus 6 is 5, right? So it's modulus of minus 5, which is 5, also multiple of 5. Then we know here, so even 1 comma 11, and then 1 comma 16. So are there any more? So no. Next, let's try with 2. So 2 and 2. Then 2 with 7. Then 2 with 12. And then 2 with 17. You subtract them, you get 15. Then we come to 3. So 3 with 3, of course. Then 3 with 8. We subtract, you get 5. Then 3 with 13. And then 3 with 18, but 18 is not there. So 3 ends here. Then comes 4. So 4 with 4. 4 with 9. And then 4 with 14. So nothing more than 5. So and so on. Okay, so you list all of these. So 5, 5, then 5, 5, 5, 10. Okay, then for 5, even 5, 0 will also be here, because 5 minus 0 is a multiple of 5. So 5, 10, then 5, 15, then 6. So already you're seeing here that it becomes very, very long. So 6, 0, then 6, this will be 11. or 6 6 also, no, not 6 0, so 6 6 here, because you subtract 6 and 6 you get 0, a multiple of 5, then 6 11, then 6 16, then you take 7, so 7 7, 7 12, and 7 17. So all other elements 8 8 8, 8 13, then 8 18, not there, then 9, so 9 9, 9 14, then 10, so see, you see it goes on everywhere, so 10, so 10 will be 0, then 10 10, I think 10, even 10 5, so 10 5, then 10 10, and 10 15. Okay, so if you list all of them until the last one 17, so 17 will be 17 17, then okay, so here, actually I'm missing some values here, even 7 2, right, will work here, because it is a multiple of 5, 7 minus 2, so even 8 3. Okay, so but what's important to see here is this, so is it reflexive? Yes, because I see all these elements 0 0, 1 1, 2 2, 3 3, all this 5 5, 6 6, 7 7, 8 8, 9 9 till 17 17, all these belong to R. So we can say that this R is reflexive. But seeing that it's too long, so let's try to prove it by using a general proof. Okay, we start like this. So we say for any A belonging to A, suppose we take any element A of this set A. So that means any number from 0 to 17, a whole number. Will AA always belong to R? That means, will A minus A, modulus of this, will it always be a multiple of 5? And the answer is yes, because whatever the value of A minus A is always 0. So I get this 0, then write down, which is a multiple of 5, so always. Because 0, you can write it as 5 times some integer, and that integer is 0. 5 is a multiple of 5. Why? Because you can write it as 5 times some integer, and that is 1. So this is a multiple of 5. Therefore, we can say, from here, you can imply that AA belongs to the relation R, and so R is reflexive. Okay, so that's very short. Then, now we prove for symmetric. So we start for symmetric by this. So if you have the condition that if AB belongs to R, okay, for some AB, so these A and B, they are elements from the set A, then can we prove that even BA will belong to R? So that's the question. So let's start. So we proceed step by step here. If AB belongs to R, then this means that A minus B is a multiple of 5. So multiple of 5. Then this means that even A minus, I think this one we can write it simply like this. So even B minus A will be a multiple of 5. Now why is this? So the reason here is simply because, so since modulus of B minus A is equal to modulus of A minus B, okay, because B minus A and A minus B, they differ only in sign, right? If this is positive, this is negative, but then here we're taking the absolute value or the modulus of both sides, so both sides will be positive, but the magnitude is the same. So these are equal. So if this is a multiple of 5, then even B minus A will be a multiple of 5. So from here we can conclude that BA then belongs to R, so therefore R is symmetric. So that's it for symmetry. Then the last one for transitivity. So we start with the if condition. If AB and BC belong to R, and this is for A, B, C, these three are from A. So if these two belong to R, so this implies that A minus B and B minus C is a multiple of R multiples of 5, because we're talking about both of them. So R multiples of 5. If you remember, there was one question above this where we talk about the relation R having element AB if A minus B is a multiple of 4. And we remember in that case when we took the condition for transitivity, we had the A, B and the BC, and we had A minus B is a multiple of 4, and we also had B minus C is a multiple of 4. So both these are multiples of 4. And in order to get A minus C, what we did was we added A minus B and B minus C, because in that case then A minus B plus B minus C, then the B will go and you'll have A minus C. But here we cannot use that directly because we have the absolute value here, the modulus. So A minus B plus B minus C may not be A minus C. Okay, so we don't know that yet. So here we find out the value of these two separately. Okay, but we try to remove first the modulus. So I get here A minus B and B minus C, they are multiples of 5. So if the number with the modulus is multiple of 5, then even without the modulus it will be multiple of 5, because the difference between A minus B and A minus B modulus is the number is the same. If this is minus 5, this will be plus 5, right? So if this is multiple of 5, then even this one will be multiple of 5. So both have to be multiples of 5. So remove the modulus, and now if A minus B is a multiple of 5, then A minus B is of the form, so is equal to 5 times some integer m, and B minus C will be equal to 5 times some integer n. So you write down m and n, or you can write down for some mn belong to the set z, the set of integers. It's like this. Suppose I say that 35 is a multiple of 5. I can say that 35 is a multiple of 5 because 35 can be written as 5 times m, and that m in this case is how much? 7. So 5 times 7. Okay, so for any multiple of 5, it is always equal to 5 times some integer m. So that value m depends on the number that we take. So in this case also, so this m and n here, so they can be any value depending on the A minus B and B minus C. But they're always of this form, 5m or 5n. So now that we have removed the modulus here, we add these two. So I'll get here implies A minus B plus B minus C is equal to 5m, 5n. This is 5m, this is 5n. This gives me A minus C, the B cancels, is equal to, from these two we take common 5 and we get m plus n. So this means that A minus C is a multiple of 5, because now even this A minus C, you see we've written it as, so A minus C is equal to 5 times some integer here, and that integer in this case is m plus n. So that means it is a multiple of 5. So multiple of 5 here. So if without the modulus it is a multiple of 5, then even with the modulus it will still be a multiple of 5, because all that changes is the sign if it is negative. So and if a minus c is a multiple of 5, we can conclude that a c belong to R. So therefore R is transitive. So that's number 1. Then question number 2, R equal, okay, now no, we have still this second part of the question left. So we have proved that R is reflexive, symmetric, transitive. So we say that, so hence R is an equivalence relation because it is all the 3. The second part of the question says find the set of all elements related to 2 in each case. So in each case, so in question 1, what are the elements related to 2? So now, so when will A relate to B in this question 1? That means it's like I'm asking, when will AB belong to R? Because if AB belongs to R, then we mean that A is related to B. In the first set there's A, in the second set there's B, and then AB, they are related by some rule. Okay, so A will be related to B if A minus B is a multiple of 5. So in this case then, we want to find, we're given that one of these two, for example, so the number B, we're given to be 2, because here it says that the set of all elements related to 2. Okay, so if B is 2, what are those A's that relate to 2? I can give one example. One example is 7. 7 relates to 2, is related to 2 because 7, 2 belong to R, because 7 minus 2 is a multiple of 5. So what numbers work in this way? So 7 works, 2 works because 2 minus 2 is 0, a multiple of 5, then 12. So actually all these that we have listed here, all these numbers. So am I missing something? 2, 2, 2, 7, then 2, 12, and 2, 17. So apart from these, there are no other elements that related to, that when subtracted with 2 get an, so a multiple of 5. So we get 0, 5, 10, 15. Okay, so find the set of all elements related to in each case. That'll be 2 itself, 7, 12, and 17. So let's write the answer. So we write it like this. We list all the elements that related to. So now, so 2 minus 2 modulus is 0, a multiple of 5. 2 minus 7, so is 0, or we can even say which is equal to 2. 7 minus 2, this is equal to 5, a multiple of 5, right, the same. Then even 2 minus 12, so 12 minus 2, same, we get 10, a multiple of 5. Then finally 2 minus 17 equals 17 minus 2, this is 15, which is also a multiple of 5. So therefore from these we see that 2 and the elements, so 2, 2 belong to R, so 2, 7, and even 7, 2 belong to R, then 2, 12, 2 also belong to R, then 217, 2 belong to R. So therefore the required, so they ask the set, find the set. So we collect all those elements that are related to, therefore the required set, let's write the whole thing, the set of all elements related to 2 is equal to, so that's 2, that's 7, that's 12, and that's 17. So that's question number 1. Then question 2, R equals AB, A equal B. This is easier. So R equal to AB, let me just write the relation again. So R equals AB, and question is if A equal to B. So let's prove for reflexive. So for A belong to A, so this means for any A belong to A is equal to A. So this implies that AA belongs to R. You see, because when will AB belong to R here? If A is equal to B, if the first element here is equal to the second. That means automatically it will be true for AA, because A is equal to A. So this means that all elements here in this set will, all these elements AA will belong to the relation R. So therefore R is reflexive. Then what about for symmetry? So we start with the condition if AB belong to R for elements AB from the set A. So the same set A that we used in question 1. This gives me, so this implies that A is equal to B. This is the condition. If AB belongs to R, it means that A equals B. And I want to prove here that BA belong to R. Okay, so when will BA belong to R? When B equals A. When we switch the sides, we switch the positions of A and B. So can we say from A equal B, can we say that B equal A? So that's obviously true, right? If A equals B, then B equals A. That means here this flows logically, and we get from AB belong to R, we get BA belongs to R. So therefore R is symmetric. Then transitive. So we start with the condition if AB and BC belong to R for A, B, C. So these elements are from the set A. This implies that if AB belong to R means that A equals B, and BC belong to R means that B equals C. So can I say from these two that A equals C? Yes, because A and C are both equal to B. So that means A is equal to C. And if A is equal to C, then according to the given relation, AC belongs to R, and therefore R is transitive. And hence from all the three, hence R is an equivalence relation. In part 2. So now, what elements relate to 2 in this case? So according to this relation here, A will relate to B. That means AB will belong to R if A equal to B. Okay, so what will work for 2 then? What number will relate to 2 in this case? That means what is that number here that will be equal to 2? If this is A, B, A equals B. So what is that number that is equal to 2. Obviously it's just 2 itself, nothing else, right? Not 5, not 7. So in this question here, the set of all elements that relate to 2 is only the singleton set 2. So only the element 2 relates to 2. Let's write down the answer. So we have here now 2 equal to 2. So this means 2 belong to R only. So I think here we have to mention somehow that this doesn't work for any other number from 0 to 17. 2 belongs to R. Then we can say and A is not equal to 2 for any other value of A belongs to A. So it works only for A equal to 2. So therefore we only have here the required set, or the set of all elements that are related to 2 is only 2 and nothing else. Okay, because if we list only this 2 here, then it's like we haven't checked all other elements. So we're mentioning here that it works for 2 and for nothing else, so that's why only the element 2. So this will be the answer for number 2.